What is utility maximization problem? It's an optimization problem. So we have an objective function, which is the sum of everybody's utility function. So for each user I, we have a utility function u sub I, which depends on some arguments. Now these arguments could be, say, throughput at the application layer, or rate at the physical layer. Later in lecture 13, soon we'll be talking about different layers and the different metrics of quality on different layers. It could also be delay. It could be jitter, which is the variation delay. It could be energy you spend. It could be the distortion of your video. It could be any of these. Although in most of our lectures we'll be looking at a rate or throughput in the argument. But in general, this is a function. Whether it's an increasing or concave function or not, we'll say a few words about that in a minute. And then you're going to sum up across all the users of the utilities. This is the sum utility, or the so-called network utility. Okay. A network utility maximization, or in short, NUM. We'll come back to this a few more times later in this course. That's the objective function. What about constraints? There can be all kinds of constraints. Technological constraints. For example, a router cannot support both large number of degree and large number of bandwidth per degree. It could be economic constraints. Okay, for example, I'm not willing to pay for a certain cost in order to provide that much bandwidth supply. And by the way, when we talk about the word bandwidth, okay, we often actually mean capacity in bits per second, rather than the width of the frequency band being used. Okay, even though a wider band, other factors remaining constant, implies a bigger capacity, but these are two physically, conceptually different terms. But so it happens, increasingly a lot of people use the word bandwidth. I guess it's a cooler name than the word capacity, so sometimes we stick to that incorrect terminology because it's used almost universally. Now, what about the variables? Well, if these depends on what's your argument in the objective function. Okay, if these are the arguments, maybe your variables could be the rates and throughputs themselves, or it could be some other design factor that will impact these different metrics. So maximizing the summation of utility function of some arguments is subject to some kind of constraint that says the variables denoted by some vector x and y live in certain constraint space x and y and so on. Now, good to formulate and try to solve, hopefully distributively, of many of these problems. So let's look at this utility function each term. Okay, let's say the argument is xi, could be, say, the data rate for a particular end user I, and the shape of the function is denoted by this function u sub I. So what kind of function could this be? Now, here you see three functions curves here in this plot. Ux over x is a single variable function. This function a is let's say a logarithmic function. We'll see that there is a special fairness notion associated with log functions in a minute. So it is quite nice. It's smooth, increasing, and concave. But you see this curve B here is actually not smooth because there's a jump at this point. Below this point, you get no utility. Above this point, you get a strictly positive constant utility. Okay, so there's a jumping point. Now, graph C is interesting. It's got some concave, convex part, and then it becomes concave to the point of bending completely flat, meaning that you give me more x, it doesn't increase my utility anymore. So it goes through a convex part, then it went through a concave part, including part of which that is completely flat. So not only the arguments of the utility function can be of various strengths, the shape can also be quite different. Okay, so in particular, is it smooth? We often deal with smooth functions. In fact, in all examples, you will see it will be smooth, but it doesn't have to be. Is it increasing? Pretty much always increasing, because we're talking about something good. It's a utility function. If you're talking about something that measures how bad it is, against some argument, maybe the answer is different. And third, is it concave or not? Now, increasing or not is talking about the first derivative of the utility function. We say, it is non-negative. What about concavity or convexity? That's talking about the second derivative. Okay, so concave means that it is smaller than or equal to 0, whereas convex means, as you may recall from lecture 4, that the second derivative is bigger than or equal to 0. Now, of course, this is talking about a single variable. If a multivariable function, then this is a gradient vector, and these second derivatives is not a scalar anymore, but the Hessian matrix. Again, back in lecture number 4. So, is the second derivative positive or negative? By the law of diminishing marginal return, which roughly speaking says that, okay, as the argument becomes bigger and bigger, eventually, even if you get happier and happier, the rate with which you become happier will be going down. So, for example, this kind of function is still going up, up, up. It never drops, but how fast you go as a function of a unit increase in the x-axis, that slows down. Okay? In other words, the second derivative is negative. Okay? It's an increasing function, but the rate of increase is actually negative. So this is usually the case as a concave function, but it doesn't have to be concave at the beginning. It says eventually it will bend over, but before eventually it can go actually like convex and then concave with inflection point, like what we observe in some of lecture 7, lecture 8's curves in diffusion models, okay, and some of the other influence models in the crowd. So you can also have a sigmoidal function with both convex and concave part. In general, if it's smooth, increasing, and concave, then it's a much nicer function to deal with mathematically. Where do these utilities functions come from? Usually there are 3 ways. One is you can run an experiment with real human beings in a focus group study. You put them in a sofa, give them pizza, and then say, well, please watch these videos or listen to these voice calls, and then you rank them, you rate them 1 to 5 stars, and then you vary the different kind of voice calls and videos you present to them. So these lead to often what's called MOS score, mean opinion survey score. Okay, you run a psychological experiment. The second reason why certain utility functions are picked is because of what they represent in demand function. Okay, utility function and demand function in some sense are 2 sides of the same coin, because we're going to model individual decision making as a net utility maximization, very similar to what we saw in lecture 2 with the auction modeled as a game, where we say that each individual here says, I will get this much utility. Okay, I'm user I, UI of xi, good. But this is not free lunch. There is no free lunch. I have to pay something. For example, pi per unit of whatever I'm getting, say bandwidth or rates, bits per second. Okay, so for each bits per second, I have to pay a unit price pi, and I'm getting this much xi in volume. So the total cost to me is pi times xi. This is how much I'm getting. This is how much I'm paying. The difference is net utility, and that is what I would like to maximize over my individual choice xi. Okay, so in the market, you give me the price. I react to the price by picking the xi. Well, if this u is a nice function like smooth, increasing, and concave, then this is a nice concave maximization xi. Concave part, a linear part. So we can just take derivative and say u prime of x, suppressing the subscript I for simplicity notation, okay, minus a p. That's the derivative, and let it be 0. That means u prime of x equals p. If a particular x satisfies this equation, call that x star, then that is the induced demand induced by this price p given to me. And it turns out that utility's first derivative is an invertible and a decreasing function because of our model of utility function. So x star is u prime inverse as a decreasing function of the price p. So we call this u prime inverse demand function d. So d is a u prime inverse. So give me a utility function, take the derivative, invert it, you got demand function. Give me demand function, I can also reverse engineer the utility functions. Coming this way from utility to demand function, you can do a simple exercise of our alpha fair utility function coming up. A particular special case is just utility being log of x. Okay. Then the resulting demand function is just 1 over p. Can easily convince self about that. And then in lecture 14, we will talk about the other direction. Give me a demand function. I figure out, then try to reverse engineer the underlying utility function. And the key concept in modeling demand is so-called demand elasticity. Okay, it's essentially your price sensitivity. We know that demand is a function of price p, and if I look at the derivative, okay, demand may depend on other things too. So the partial derivative of demand as a function of p over p. So partial dp partial p. This is sort of like my price sensitivity, right? Okay, if price goes up, how much is my demand dropping? But I also want to normalize it. So I'm going to normalize it by dp over p. This normalized version of price sensitivity is called a demand elasticity and often represented by the symbol eta. Okay. For example, what is eta of log utility function? We know the demand elasticity is just 1 over p. You plug in this normalized partial derivative against p, you see that eta is actually exactly 1, which is quite interesting because it's actually independent of p. Okay. So the second way to model utility is through so-called demand function. Okay. The third way is through your concern on fairness. Again, later in lecture 20, we'll devote the whole lecture on different notions to quantify fairness. But today we start the introduction there of that quantitative approach to fairness. And this introduction says that there is a family of functions called alpha fair utility functions. It's not a function, it's actually a whole family of functions. Okay, and it's parameterized by a simple single scalar alpha greater than or equal to 0. That's why it's called alpha fair utility function. What is that alpha fair utility function? Well, first, let's define what is an alpha fair resource allocation. We say, suppose you tell me there is a vector x, let's just say x, okay? It's a vector. Allocates some good resources x1, x2, up to xn among the n users competing against each other. And I say that this is a particular function vector, is that alpha fair allocation vector if, here's the definition, okay? If for any other feasible vector y, all such y, if I look at the difference for each user between getting something from x vector versus getting from the y allocation, and then I normalize it by xi to the power alpha. That's where the alpha comes in. That's some kind of alpha parameterized normalization of the difference in drifting away from x allocation to y allocation. And then I look at the joint impact, the collective impact to all the users in the system, summing over I. If this summation, which is a single scalar, is negative, okay, less than or equal to 0, then I say this vector x is alpha fair vector. Now, that's a mouthful for definition. Let's parse it again. We say a vector x is alpha fair if for all any other feasible allocation y, you can't give me an infeasible allocation and ask me to compare, okay? Any other feasible allocation y. If I look at the collective alpha parameterized normalized drift from x to such vector y is always a bad thing, okay? The sum is negative. Then I say this vector indeed is alpha fair allocation. All right, now you can disagree with the definition, but it turns out to be a useful definition and therefore a good definition. So what about our utility function? This is a vector, not a function. Well, it turns out that without proving this, we just state the result that says, if you maximize the following parameterized utility function, parameterized by alpha, so I'm writing alpha in the subscript for this utility function as a function of x. If you maximize this function, what does it look like? Well, it's a branching definition. It looks like simply x to the power 1 minus alpha over 1 minus alpha. If alpha is not 1, okay? If alpha is 1, this denominator is not defined. But you can use L'Hopital's rule and see that when alpha is 1, this actually is log of x. Okay, now I see the familiar and important special case of log utility. So if this is the definition of your utility function, then maximizing such utility function will lead to an answer, the optimizer x star, that satisfies the definition of alpha fair allocation. That's why we call this the alpha fair utility function. Another name for it is called isoelastic utility function. Okay, why isoelastic? It gets back to our notion in the last slide. Okay, in a homework problem, I think you easily verify that if you take this definition of u of x, you will see the resulting demand function. Okay, and then that implies the elasticity is actually 1 over alpha. In particular, when alpha is 1 for log utility, the corresponding demand function is just 1 over p, and the corresponding normalized demand elasticity is just 1 over alpha. It's just 1 in that case when alpha is 1. Okay, but in general, for other non-1 alphas, it's 1 over alpha as eta. That means the elasticity of demand is all independent of everything else. Okay, except the shape, this parameter alpha. That's why it's called isoelastic. Later we'll see many good uses of isoelastic or alpha fair utility function, including the following special case. When alpha is 0, what do we have? That's simple. We're just looking at the allocation itself. This is a sum allocation, for example, sum rate maximization. When alpha is 1, that's a log utility function. It turns out that it leads to what's called proportional fair. If you look at this definition here, when alpha is 1, it means that your normalization is simply xi itself. You're not trying to skew the shape by any means. And whether you like the definition or not, you can see why this is called alpha proportional fair, because proportional back to normalized by x. So when alpha is 1, you have the special case called proportional fairness. Now, when alpha is really big, for example, alpha approach infinity, then it turns out that it approaches what's called a max-min fair. Now, we'll later talk more about fairness, so let's leave it just like that for the moment and conclude this part of the video module with a simple application of this utility model. Okay, whether it comes from focus group study or fairness or demand elasticity. Apply this simple utility model to talk about a very important phenomenon called the tragedy of commons. Now, this was first formally mentioned by Lloyd a long while back, 1833, and then codified and popularized by Harding's article in 1968. Now, this article had other kinds of provocative and somewhat controversial arguments. Tragic Commons is only one small part of it. But we have seen a liberal use of this term, tragedy of commons, quite a few times in Lecture 1 when we talk about power control, interference. That's the tragedy of commons in the air. When we were in Lecture 2, okay, tragedy of commons in terms of second prize, correctly internalizing the externality imposed on other auction competitors. In Lecture, I think it was 6, okay, in voting theory, okay, the K degree of externality imposed on other voters, and the need for something like border count. And later in lecture, I think 14 for TCP, 15 for P2P, and 18 for Wi-Fi. Okay, in all these cases for tech network discussion, we will see a different manifestation of Tragic Commons. But the reason it was called Tragic Commons was because it was a thought experiment. Okay, just like this binary number experiment in Lecture 7. It says that suppose you got a piece of common grassland as the commons, okay, and there are different farmers. And each farmer says, okay, should I get another cow or not? Okay, here's a cow. Well, it looks like a mouse, but let's say it's a cow, all right? So should I get a cow or not? Well, if I get a cow, the cow's going to need to eat grass. Okay, but the cost of eating that grass is like, if there are n farmers, it's like 1 over n, proportional to that. But the benefits to me of the milk and maybe selling the cow or for its meat later down the road is one unit. Okay? So what's going on here is that if I look at my selfish maximizations, that I got a utility, okay, U of x. All right, and now I got to pay the price. Okay. That means I have a demand as a function of the price. The price is just 1 unit. Okay. And in this case, a rational farmer would say, I should get another cow. And the same argument keeps on going. I should get yet another cow, and every farmer thinks the same way. Then what would happen? Well, the tragedy of commons happens. There will be so many cows here that it leads to utilization of this grassland. Okay, and once it's overgrazed, then the grassland will eventually deplete, and the cows will die. So it's actually a bad outcome for all the farmers. This is, I guess, the 3rd time in this course encountering the situation. It's a little paradoxical that each selfish behavior actually lead to collectively the worst phenomena for every individual. So what's wrong? Well, what's wrong is that the price wasn't set right. Okay, instead of setting it to be 1, maybe you should set it to be proportional to n. And this change will lead to the demand function operating not on the price of 1, okay, but on the price of n. Okay. Now, this is another example illustrating what we call negative externality. Okay, it is externality just means that your behavior and my behavior are coupled together in this impact. It's negative because you get another cow is going to damage my prospect. And one way to so-called internalize, in contrast to externality, internalize externality, meaning that to mitigate its negative effect, is through pricing. Later in chapter 14, we look at mathematical theory in advanced material of Lagrange duality that says basically if you price properly enough, then you often can internalize the negative externality. All right, so that's a long introduction of the utility model. now going to take the utility maximization model to provide 3 reasons why usage-based pricing for internet access makes sense, and what can we do to visualize these 3 reasons. Okay, we're going to visualize these 3 reasons through 3 different demand price diagrams.